Quantum numbers and atomic orbitals. This short presentation is designed to give you a brief overview of the relationship between the quantum numbers that come out of quantum mechanical calculations and atomic orbitals that we use to describe the energies and probabilities of finding electrons in atoms. We know that the energy levels of electrons in an atom are quantized. That is, we know exactly what the energy levels of those electrons are. This experimental evidence comes from spectroscopy. But we also know that we can't know both the energy and the position of an electron. We just can't because of Heisenberg's uncertainty principle. And we also know that particles at the atomic molecular level, and particularly electrons, have wave-like properties. So all this led to the development of wave mechanics, and we use the equations derived from wave mechanics or quantum mechanics to describe both the energy of an electron, and instead of exactly where that electron will be found, we're going to describe the probability of finding that electron in a specific region of space. And we call these regions of high probability atomic orbitals. And each orbital can be described by a set of quantum numbers that are derived from quantum mechanical calculations. Now, the goal of this is not to have you memorize these quantum numbers and be able to reproduce them, but to give you an understanding of how they are used. So there are four types of quantum numbers: n, l, m sub l, and m sub s. And together they allow us to understand how the electrons are arranged in atoms, and actually they allow us to understand why the periodic table is arranged the way it is. So let's go through them. N is the principal quantum number, and it can have values of any integer, 1, 2, 3, 4, 5, and so on. L, which is the angular momentum quantum number, can have whole number values that depend on the value of n. So they start at 0 and go up to n minus 1. Similarly, m sub l, the magnetic quantum number, depends on the value of L, and it can have whole number values from minus L to plus L, as we'll see in a minute. M sub s doesn't depend on any of the quantum numbers, and it can only have values of either plus or minus a half. So let's go through a few examples. If n equals 1, the only value of L that's allowed is 0, because n minus 1 is 0. And so the only value of m sub l is also 0. And the type of orbital that these quantum numbers describe is the 1s orbital. 1 for the principal quantum number n equals 1, and s describes the orbital shape, which in this case is a sphere of electron density. If n equals 2, L can still equal 0, and m sub L will still equal 0 as well. And so the orbital type that's described by these quantum numbers is the 2s orbital. It looks like the 1s, except it's bigger, and it has a node. That is a place where there's no probability of finding the electron within the sphere of electron density. But in the n equals 2 quantum shell, there are also another value of L, and that is 1. If L equals 1, then m sub L can have three values, 1, 0, and minus 1. And these describe the p orbitals. Each of these m sub L quantum numbers describes a 2p orbital, and these orbitals are oriented mutually perpendicular to each other, like a set of x, y, z axes. And they have two lobes of electron density with a node at the nucleus. In n equals 3, L can still equal 0, m sub L 0, and 3s, the 3s orbital would be like the 2s, but now it has 2 nodes, so it's bigger. L can also equal 1 in the n equals 3 shell, which means that there are 3 allowed values of m sub L, and then these 3 values are the 3 p orbitals, and there are 3 of them, just like the 2p. But it's not important for our purposes that you memorize the structures of the d orbitals. So the question remains, why do we need to know this? What's the use of having all these quantum numbers? And how can we use them? Well, we use them to understand the idea that electrons can be described by orbitals of different shapes and definite energies. These ideas allow us to understand how elements bond and react, and they also allow us to understand the arrangement of the periodic table, as we'll see shortly. So to recap, each atomic orbital can contain a maximum of 2 electrons, and we can think of a set of quantum numbers as descriptors for electrons in an atom. And in fact, each electron in an atom has a unique set of quantum numbers. Remember m sub s? So electrons in the same orbital, which would have all the same quantum numbers except m sub s, which would be either plus a half or minus a half. And now onto the periodic table.